So now that we've seen some particular examples of area formulas for particular quadrilaterals and triangles and circles, we're going to look at the area formula for regular polygons, generally something that we can apply to every regular polygon that we see. So first, let's do a quick reminder and remind ourselves that a regular polygon is one where all of the sides and angles of that polygon are congruent to each other. So an equilateral triangle, a square, a regular pentagon has 5 congruent angles and 5 congruent sides. The regular hexagon has 6 congruent angles and 6 congruent sides, etc. So if we know just the side length of a regular pentagon, for example, if there's a 2 centimeter side length, how could we find the area of this pentagon? All the sides are the same, so there's something predictable about this, but it is much more difficult than, say, just knowing the side length of a square and being able to find its area. So go ahead, pause the video, do some brainstorming around what you think might be able to happen here. Come back when you're ready to see a few different pieces of terminology related to regular polygons, as well as the area formula for it. So at first glance, there's not a whole lot of ways that we can really be effective at doing much here, because all of the different things that we've seen, all of the different area formulas rely on something being perpendicular, and they rely on our objects being either triangles or quadrilaterals. So we could draw a diagonal that splits this pentagon into a triangle and a trapezoid, or at least it seems like a trapezoid here, but we still have the problem of having to figure out what the perpendicular lengths are for example, the height of this triangle, or the height of this trapezoid. There's a lot that's unknown. And so in order to find the area of a regular polygon, we actually turn to something slightly different. One of the things that is true about every regular polygon is that a regular polygon can be inscribed in a circle. It's one of those properties. And because it can be inscribed in a circle, we can talk about 3 particular things related to regular polygons that we can't about just any old polygon or 2-dimensional figure that we see. For example, the center of the circle is something we call the center of the polygon. And the radius of the circle is what we call the radius of the polygon. And that is the distance from the center to each vertex, because if the polygon is inscribed in a circle, remember that each vertex then is on the circle, so each vertex is the same distance from the center, meaning that there is a radius to this polygon. So go ahead, pause the video, copy these definitions down as well as the diagram, come back when you're ready to see one more example of terminology related to this styling of a regular polygon, and then see the area formula. So while the radius and the center of the circle are really helpful in a lot of ways, they're still not necessarily perpendicular. But now that we have a central point for this circle that is splitting this pentagon into 5 congruent triangles, because all of the radii are the same and all of the side lengths of the pentagon are the same, now we have a strategy starting to evolve. If we can find the area of one of those triangles, we can multiply it by 5. So we can talk about the distance from the center to the side. And that is a particular segment in a regular polygon, and it requires a regular polygon that we call an apothem. The apothem of a regular polygon is the distance from the center to each side. Now, we're not going to prove that the apothem is the same to each side, but all of those triangles are congruent, so it shouldn't be difficult to get to the point where we know that the height of each of those triangles, which is the length of the apothem, is congruent. So go ahead, pause the video, copy this down, come back when you're ready to see how this informs the area formula. So now we can start talking about the area of this regular polygon. So for example, in just this triangle here, the area is 1/2 base times height. Well, the base of that is the length of the side, which we normally call S in a regular polygon. So that is 1/2 times S times the length of the apothem, which is often abbreviated as lowercase a, not to be confused with uppercase A, which is the variable given to area or surface area. So that one triangle is 1/2 times S times A. Well, we have a certain number of sides in a regular polygon. In this case, we have 5. But it doesn't necessarily have to be a pentagon. We could do this with a dodecagon and still end up with 12 congruent triangles. So the variable that we give, as we've seen before, to the number of sides of a polygon is n. So the whole thing is 1/2 base times height times the number of triangles that are made, 1 for each side. So 1/2 S times A times n, but the side length times the number of sides gives us the sum of all of the sides of the polygon, which is just the perimeter. And that brings us to the area formula for a regular polygon. The area of a regular polygon is 1/2 times perimeter times the length of the apothem. Or it's 1/2 times the number of sides times the side length times the length of the apothem. So go ahead, pause the video, copy this down, come back when you're ready to do 2 practice problems to wrap the video up. So it really is just as simple as that. It's based on the triangle formula. Because we started with triangles, we can create congruent triangles within a regular polygon because the radii are all the same and all the side lengths are the same. Again, this is specific to regular polygons. So it should make sense that the area formula for a regular polygon looks very similar to the area formula for a triangle. So we just need to plug in these values into the formula and we can calculate the area. So in each of these 2 regular polygons, in a minute, you're going to pause the video and calculate their areas. The 4 centimeters and the 3 inches are the sides of a single side of the regular polygons, and the 3.5 centimeters and the 3.6 inches are the lengths of the apothems. So go ahead, pause the video, calculate the area of these 2 polygons, come back when you're ready to see the answers, and end the video. So in the regular hexagon, we have a side length of 4, and we have 6 sides. So in 1/2 perimeter times area, or times apothem, I should say, that is 1/2 times 4 times 6, which is the perimeter, so 24, times the length of the apothem, which is 3.5, or 12 times 3.5, which gives us 42 square centimeters. In the regular octagon at the right, let's use 1/2 NSA. That is 1/2 times the number of sides in an octagon, which is 8, times the side length, which is 3, times the apothem, which is 3.6. And when we multiply 1/2 times 8 times 3 times 3.6, we end up with an area of 43.2 square inches. So again, quick review. The area of a regular polygon is based on the fact that the polygon can be inscribed in a circle, giving the polygon a center, which is the center of the circle, and the polygon a radius. And because the radii of circles are the same, we can talk about the height of each one of those triangles, something we call the apothem, which gives us the area formula 1/2 perimeter times the length of the apothem, or 1/2 the number of sides times the side length times the length of the apothem. And again, this only works for regular polygons, but that is the area formula.